Assalamualaikum warahmatullahi wabarakatuh. My name is Natasha Amirah binti Aziz and my supervisor is Dr. Farah Shaida binti Muhammad Saleh. Before I start my presentation, I would like to inform that my project title has been changed, which is to study an optimization of 3D printing process parameter on printed part of PLA, HK, micro and nanoparticle composite material using design of experiment. So this is my presentation outline, started with the introduction, literature review, problem statement, objective, scope and limitation, methodology, and the last one will be the expected result. 3D printing has become a hotspot widely used worldwide. It is also called additive manufacturing because the process involves the addition of material to an object instead of subtracting it. 3D printing technologies is popular in every sector, including industry and research laboratories, such as healthcare, aviation, and more. The object was created a three-dimensional shape, layer by layer, through the addition process of material from a computer-aided design model until the desired shape was printed. So there are various types of 3D printed systems with different processes. In this experiment, the scaffold composite is produced using the fused deposition modeling (FDM), also known as fused filament fabrication (FFF). Both techniques use the same method, where the prototypes are printed by extruding the molten thermoplastic filament through a nozzle. According to Farah et al., the rate of crystallinity in polymer is important property to determine its physical and mechanical properties. Crystallinity is the amount of crystal area in a polymer that play a role in changing the structure from liquid to solid. So, there are three structural positions in PLA crystal, which are alpha, beta, and gamma. Alpha form usually occur in melt or cold crystallization and is used to form the beta form through mechanical stretching at high temperature. It also has low thermal stability because its melting temperature is 10 degrees Celsius lower than the alpha form. The last one is gamma form. It is used to develop a hexamethylbenzene structure consisting of two antiparallel chains in a crystal cell. The new properties of PLA are based on the type of optical isomer, either L-lactic acid or D-lactic acid. Figure 1 shows the different isomers affect the thermal properties of PLA, like molecular number, Mn, glass transition temperature, Tg, melting temperature, Tm, enthalpy, H, and crystallization temperature, Tc. It shows that the value of Tg and Tm increase in relation to Mn for both types of isomer, except for the sample with high polydispersity index, PDI. PDI is a measure of the molecular weight distribution of a polymer, or it also can be defined as mW per Mn. Hydroxyapatite, HA, is a bioactive ceramic that has a high chemical similarity to inorganic mineral components like bone and tip. Therefore, it is always developed in bone tissue engineering because it has great behavior such as bioactivity and biocompatibility. Figure 2 shows the result of mechanical properties of your medallions for both composite size. PLA nano HA has a higher ultimate strength than PLA micro HA with the mean value of 4 plus minus 0.2 gigapascal and 2.8 plus minus 0.2 gigapascal respectively. Therefore, the young modulus of human bone tissue is close to the biocomposite with nano HA in the range of 3 to 5 gigapascal. A 3-point fracture test was performed to verify the previous result. Figure 3 shows the nanoparticle has a better interaction with polymer matrix compared to microparticles. Any electron microscope SEM was conducted to observe the brittle fracture after performing the 3-point bending test. Figure 4 shows that microparticles produce a lot of agglomerates performing around 100 micrometer in diameter while nanoparticle has less than 10 micrometer, where they show a better distribution in the polymer matrix. According to Akandi, FDM technology is used to fabricate some test parts with different type of process parameter, which are layer thickness, field density, and speed of deposition. The objective of the experiment is to choose the best process parameter that can be used to produce a good dimensional accuracy and surface finish part. The method used to investigate the optimal factor level is DOE, which is design of experiment, because it is reported to be more efficient in process characterization and factor screening. Figure 5 shows the setting of process factor during the experiment. Based on the result of experiment, the optimal parameter for dimensional accuracy are height layer thickness 0.5 mm, low infill density 20%, and low speed of deposition 16 meter per second. Hernandez et al. Analyzed some mechanical properties such as compressive strength, fracture at 4 points, and tensile strength. Each property uses a different type of ASTM standard. The specimens were made from ABS in different orientation. So this experiment used 45 samples with 15 samples for each mechanical properties used to print in 5 orientations. Based on the figure 6, the sample printed at 0 degree in the XY plane obtained the higher value in compressive and fracture strength, which are 59.3 megapascal and 122 megapascal respectively. The strongest sample intention was printed at 90 degree in the XY plane with the highest tensile strength 10.8 megapascal and low tensile module 586 megapascal. Therefore, it can be concluded the printing at 0 degree in the XY plane is able to increase the compressive and fracture strength, while printing at 90 degree in the XY plane will increase the tensile strength compared to other orientations. So there are some problems obtained from the previous article. The first one is PLA materials are limited in some applications due to their disadvantages such as poor mechanical behavior, brittleness, low crystallinity, and low crystallization speed. Therefore, PLA has been modified physically and chemically to expand its use by improving its properties and quality. Next, the number of shells and the extrusion temperature required further analysis to improve dimensional accuracy, because most existing studies only consider 2 or 3 common parameters. Therefore, more parameters such as filling pattern, nozzle diameter, and extrusion temperature need to be studied to get accurate results. In addition, the study of compressive strength and fracture strength also less compared to tensile strength, because fracture strength is more complex than the other mechanical behavior. The experiment conducted usually use different combination of printing parameters, which is quite difficult to obtain the valid result. Therefore, the author suggests to use specific value to accurately summarize the result. Based on the stated problem, the objectives of this project are: firstly, to produce filament from the combination of materials PLA and HA, which is there are 2 sizes of HA used, micro and nanoparticles. Second is to study the effect of printing parameter on the mechanical behavior of the product. And the last one is to determine the optimal printing parameter that can be used to get the best result in mechanical behavior. This study is conducted to compare the effect of printing parameter on products made from PLA and HA, micro and nano size composite materials. There are 2 samples with 3 different process parameters, which are layer height, nozzle speed, and temperature, will be examined to determine the best option to produce a good part. The limitation of the project is that the number of parameters to be studied is limited to 3 because the limited use of the laboratory causes a lack of time to study other parameters. The experiment begins with producing a filament. Filaments are made from organic and inorganic raw materials, namely PLA and HA. 2 types of filament will be produced because the HA used is in micro and nanoparticles. Therefore, this raw material will go through several process steps and be developed using a square extruder with a certain diameter. Next, print parameters such as layer height, nozzle speed, and temperature will be evaluated using response surface methodology, RSM, to study their effect on SEM, surface roughness, and mechanical behavior. Then DOE is used to collect the data to create a design matrix that will show the combination of high and low level for each print parameter. Lastly, design expert software is used to obtain the optimal printing parameter numerically and graphically. Numerical optimization is used to find the best parameter of the model, while graphical optimization will show the reasonable result can be obtained. Figure 6 shows the result obtained from the previous research has a preliminary result. Based on the discussion, 4 levels of nozzle temperature is applied to print the PLA specimen, which are 200 degrees Celsius, 205 degrees Celsius, 215 degrees Celsius, and 230 degrees Celsius. The graph obtained is the relationship between the tensile modulus and temperature, where the results show the optimum nozzle temperature to get the best tensile modulus is set to be at 215 degrees Celsius. Below the optimum nozzle temperature, the filament cannot melt sufficiently, causing a weak bond between the particles and the layer because the maximum viscosity fails to be provided. But if the temperature is set too high, it produces almost a Newtonian fluid where the viscosity is low. Therefore, it requires longer cooling time. It affects the crystallinity degree as well. It can be concluded that the nozzle temperature gives a significant effect on the mechanical behavior of the product and only slightly affected the mass of the product. So this is my Gantt chart showing all the process flow and planning for my project. The dark purple showing the planning and the light purple show the actual time that I complete for each task. So that's all from me. Hopefully all panelists enjoying my presentation. Thank you.